Now we have to make a AVL tree by using the given nodes. So first step is we will make the nodes as a binary search tree nodes. That is, we will add nodes the same way we did in binary search tree by repeated comparisons. First step is that. Alright. Okay. So now let's create 40. So there is no node, the root node is null. So we will just add 40. So my 40 is the root node currently. Alright. Now I have to add 20. Also we will here calculate balancing factor. So for 40 the balancing factor is 0 right now. Alright. So now let's add 20 here. So when I add 20, it will go on the left side of 40 because the left side tree contains all the values which are less than the root. Hence we will add 20 here. Alright. Now let's go to 10. Also let's calculate the balancing factor again. The balancing factor for the leaf nodes are always 0. So for 20 it will be 0. For 40 it will be the height of the left subtree is 1 minus the height of the right subtree which is 0. So 1 minus 0 which is equal to 1. Okay. Now I have to add 10. So 10 will go on the left subtree of 40 because it is less than 40, and also it will go on the left subtree of 20 because it is less than 20. So here I have 10. Alright. Now we will again calculate our balancing factor. So for leaf node it is always 0, so 0. For 20, let's see the new balancing factor that will come. It is left subtree height is just 1 minus right subtree height which is 0, so it will be 1. For 40, let's calculate again. For 40 the balancing factor will be left height is 2 minus right height which is 0, which is equal to 2. Now ring. So here 0 is valid for AVL. 1 is also a valid balancing factor for AVL, but 2 it is not, because a valid balancing factor, let us write here, valid balancing factor lies in what range? It lies in the range 1 to minus 1. This is the range in which a valid balancing factor shall lie. So now we have to identify the case and apply rotation. That is the key point in AVL. These are the key points in AVL, because in binary search tree you do comparison and add nodes. That's same what we did here. We added binary search tree nodes by making comparisons, but also now we will check for balancing. At each step we are checking for balancing, and as we found it unbalanced, we have to identify the case and perform rotation on it. These are the special cases that we perform on AVL trees. Okay. Now let's identify the case, which case it is. Here if you see, this is present at the right, this is present at the left of left. So it is present at left of left. So what case it is? It is basically LL case. Which case it is? It is LL case here, because it is present at left of left. This is LL case. Now in the LL case, if we remember what we do, we perform a right rotation. What we do? We perform right rotation. So let's perform the right rotation here. So our right rotation will, in the left LL case we perform right rotation, in the RR case we perform left rotation. So this is how we will rotate. Now also, what do we mean by rotating it? Let's understand in detail. So we are saying from now on that we are rotating, we are doing right rotation. What does it mean? It means that when I do right rotation for this hole, then this node is stretched here. It is put at a lower level. Okay, we are stretching it like down, and this node and this node are stretched upwards. we are pushing it upwards. So this is how the balancing happens. So when I say right rotation, pick the first node, stretch it here, bring it down, and these two nodes, we bring them up. Alright, so it will look like, on performing a right rotation, how it will look like. It will look like we will have 20 here, I will have 10 here, and I will have 40 here. Alright, now let's calculate the balancing factor again. So for it, leaf node 0 0, and the height of left subtree for 20 is 1, right subtree is 1, so it is 0. Now again it is balanced. So now we will leave it at like this. Now let us go to the next node that we have to insert, which is 25. Okay, now I have to insert 25 here. So for inserting 25, what we have to do? We have to first add the node just like a normal bind to search tree. So 25, it is greater than 20, so I will add it to the right part. Okay, now it is less than 40, 25 is less than 40, so I will add it here. Alright, great. So we have made the attachments. Okay, now let's check the balancing. Okay, so now for checking the balancing, let's calculate the balancing factor again. For this node it will be 0. For this it will be the height of the left subtree is 1 minus height of the right subtree is 0, so it will be 1. For this 10 it will be 0, and for 20 it will be the height of left subtree is 1 and the height of the right subtree is 2. So this is comes out to be minus 1. Hence this is balanced right now. Okay, this is balanced. Minus 1 is valid, 1 is valid, zeros are valid, of course. Okay. Now let us add a new node here. So the new node which we have to add is 30. Now let's add 30 here. So 20, 30 is greater than 20, so the right part of it. Now 40, 30 is less than 40, so the left part of it. 25, 30 is greater than 25, so the right part of it, and here it comes. So we have 30 here. Great. Now we need to do the calculation of balancing factor again. So here for 30, the balancing factor will be 0, it is a leaf node. For 25, it will be 0 for the left, 1 for the right, it is minus 1. Okay. For 40, what will be the new? For 40, the new balancing factor will be on the left, the height is 2, minus on the right, the height is 0. So it is 2. Okay. For 10, it is 0 only because there are no, it is a leaf node simply, or it has no children. For 20, it will be the left height is 1, the height of the left subtree, and the height of the right subtree is 1, 2, 3. So 1 minus 3, which is equal to minus 2. So now there is a clash. What is the clash? We have got two invalid balancing factors for a evil tree. So what shall we do? Minus 1 is valid, 0 is valid, 0 is valid, 2 is not valid. Now minus 2 is valid. Okay. So we will pick, in case of clash, we will pick the balancing, we will pick the node which is closest and sister of the newly added node, or I can also say the first ancestor who got unbalanced, as I have mentioned over here, or I can also say This is not great. Okay, or I can also say here the first node which got unbalanced. The first node which got unbalanced. Which got unbalanced. Okay. Now we have the balancing factor issue. Now what we have to do? Now we have to identify the now we have to identify the case. Okay, let's us identify the case. So this is the node at which the unbalancing happened first, or the closest, as it is closest to 40 is closest to 30, 20 is further. Okay, now what I shall do, I'll just assume I will just check for the case. So 40, it is at the right, sorry, it is at the left, and 25, it is at the right. So what case it is? It is a case of LR. So it is a LR case, in which what we do? This is a LR case. Now in a LR case, what we do is, in step 1, we perform a right rotation, sorry, we perform left rotation, LR case, first left rotation on last two nodes of the set. On last two nodes of the set of 3 nodes. Then we perform step 2. Then we perform a right rotation on whole set. Why I'm saying the set? Because I don't have to perform, suppose here it is 40, here it is 25, here it is 30, here it was X, here it was Y. So you will perform left rotation here. It doesn't like that. It doesn't work like that you will perform X and Y. The set is corresponding of these 3 nodes. These 3 nodes are corresponding of the set. So you have to apply left rotation on these 2 nodes in this case. Okay. So performing left rotation here. So on the last 2 nodes of the set, we will perform left rotation. Now what does left rotation mean? Left rotation simply means that, as we discussed for the right rotation, the left rotation is same. When I perform left rotation, I will stretch this node downwards. This will come downwards and this will go upwards. This will go upwards. So for the left rotation, this node will come downwards here, and this node will go up. We will push it up and it will come here. So the new will look like somewhat like this. Okay. So now let's perform the operation. So 20, first we do the step 1. 20 will do, the upper part will be like this only, 20, 10, 40, 30 will come above as we said, and 25 will be on the left, 25 will come over here, here will be 30, here will be 25. Okay, now we have to perform the right rotation. Now we have performed the left rotation. Now we will perform the right rotation. So for right rotation, we will perform this right rotation on this. As it is LR case. So first we perform left rotation on the last 2 nodes of the set, then we perform right rotation. So performing right rotation, we will get, this will be right rotation, so this will be downwards, these 2 nodes will be pushed upwards. So the new will look like somewhat this and this, because this will come, this node will come here, this both nodes are pushed upwards, this one is pushed down. Okay, so the new will look like, so after the right rotation, this was the left of last 2, And then we perform right rotation, which will look like we will have 20 as it is, we will have 10 as it is, we will have 30 in the middle, we will have 25 here, and we will have 40 here. Now let's recalculate the balancing factor. So for the leaf node it is 0 0 0. For this it will be 0, that is height of the left subtree, height of the right subtree, which is equal to 0. For this it will be height of the left subtree, which is equal to 1, height of the right subtree, which is equal to 1 2, 1 minus 2, which is equal to minus 1, and this is completely balanced. So this is how we did it for adding 30. Now we have to add one more node, just a last node that we have to add. Also one more thing, that we could have applied a shortcut here. What shortcut we would have applied? See, here we have 30, 25, 40. What case is this? LR case. We had discussed the shortcut that attach this simply to the above node. Okay, and replace this. So 30 will come here and 40 will come here, and it's done. So 30 will come here, replace this and attach. So 30 will come here, 30 will come here, and 40 will be attached here. 25 was already attached, so no worries. So this was the direct way of doing in the diagram. Okay, now to this we will add last one, which is add 22. We have to add 22 to it. So to add 20 to it, let's add it. Where shall we add it? So 20 greater than 22. So the left part, sorry, the right part 22 will happen. 30, okay. So the left part, of course, 25, okay. So the 22 will come here. Alright. Okay, now let's calculate the balancing factor again. So we will calculate the balancing factor again. For the leaf node, it is 0. It is 0. Okay. It is 0. Okay. Now for 25 it will be height of the left minus 1, 1 minus 0, which is equal to 1. For 30 it will be, let's see, for 30 it will be height of the right, which is equal to 0 1, height of the left, which is equal to 2, which is equal to 1. Alright. For 20, let's calculate height of the left subtree, which is equal to 1, height of the right subtree, which is equal to 1, 2 and 3, so which is equal to minus 2. No, here is the alert. What happened here? 0 is valid, 1 is valid, 1 is valid, but minus 2 is invalid. Minus 2 is invalid. So we'll pick it as a, we will select this node. Why we select this node? Because it was the first node that got unbalanced. Why we select this node? Because this was the first node that got unbalanced. Okay, we selected 20 because here in this case it is the only node, but because it was the first node that got unselected, that was the first node that got unbalanced. All right. Okay, now we will have to perform now we have to perform the rotation. So this is the node. Now let's see where is the new node added with respect to it. So first is right, okay, right, then it is left, okay, then it is left. So the case where it will be RLL case. Okay, RLL case. Now we have not studied anything like RLL case, but we discussed that only using that four cases we can solve out the problem. So the key is that you have to just consider the first two letters here. Here can be L R, doesn't matter, you have to just consider first two. So as here it is, what is it is first we are going to the right, then we are going to the left, then we are going, this is RLL, but we'll consider only first two everywhere. So this RL case. Okay, so now for the RL case, this time let's use a shortcut. Why to do all the hard work? So this is a RL case, or we can do using the longer method. So let's do the longer method for better understanding, because that matters at the end. Okay, so first let us discuss what set of three nodes we will select. This is 20, this has to be selected. We will select this and we will select this. Why? Because here we see this is R, this is L, and we can't select this because we have to only select 3. So these 1, 2, 3 nodes are the ones that we select. Okay, 20, 30 and 25. Okay, now let us recall what we did in the RL case. In the RL case, what we did, the step 1 was right rotation on last two nodes of the, we have to perform right rotation on last two nodes of the set. On the second step, you have to perform left rotation on the whole set. Alright, okay, let's do it carefully because now we have children also. Alright, RL case, right rotation on the left last two nodes first, then L means left rotation on the whole. Okay, so now let's do these are the two last nodes of the set, because this is the set that we have. Okay, so these two are the last two nodes. Now we have to perform right rotation, so we will rotate it right. So right rotating means we will pull it here and we will pull it above. So basically this will come here and this will come here. Okay, so let's draw it. Here we will have 20, here we will have 10. Now here we will have 25. Okay, here we have 22. As it is, no change. Here I have 30. Here I will have 40. So let's decrease the size a little bit, it's too big. Okay, so it will be like this. Alright, so this will look like this when we perform the right rotation on the last two nodes first of all. Alright, now we have to perform left rotation on the whole set. The whole set contains, what does the whole set contains? It contains of 20, 25, 30. Correct? It contains of this 20, 25, 30. So we will perform left rotation here. So left rotation means pull this down, it will come here, and these two nodes will come above. So now let's do it. Just here we have to take care of the children. Here we have to right on last two, and here we are doing left on whole. This is the set on which we have to perform. Okay, So here we will have, this will come here above, so 25. Now the left subtree will be 20. Okay, so this node, okay, this node has to be taken care of. All right, 20 will remain as it is, 10 will come here, no problem. Okay, 25. Now we have 30 here on the right and 40 here. Okay, now we have to take care of 22. Now let's see where will 22 go. 22 is greater than 20. Okay, but it is lesser than 25, so it will go in the left subtree of 25, but on the right subtree of 20 as it is greater. So this at the end will be my tree, which will be formed after balanced BST binary search tree after addition of nodes of given nodes. And to check if it is balanced or not, we will just calculate the balancing factor once again. So 0 for the leaf nodes. Alright, for this it will be 1 minus 1, which is equal to 0. For this it will be 1 minus 0, 0 minus 1, which is equal to minus 1. And for 25 it will be the height of the left, which is equal to 2, the height of the right, which is equal to 2, so 0. So all the values are valid, hence this is our final balanced tree which we get. So this is a very important topic, and this whole process is way more important than the code. And now we will write the code. Alright.